So the classification of matter. One thing scientists like to do is we like to classify things. This is a little bit like, a kid with their building blocks, and it's like, well, we could put the blue ones here and the red ones there, or we could put the long skinny ones here regardless of their color and put the square ones over there. You can group things by different properties. And so that's what scientists do with everything. So here we're going to talk about matter. And first we have to ask, what is matter? Not what's the matter, but what is matter? Matter is anything that occupies space and has mass. So one book described it as, if you can put a sticker on it, it's matter, right? There are some things that are matter that you couldn't put a sticker on. The air in this room is matter. It occupies space. Think about a balloon, right? Blow up a balloon. What's filling the balloon? It's the air. It occupies space, and it has mass. It's a little bit challenging to weigh the air, but it does have mass. So your textbook, your desk, your chair, your body, your cat, all of those things are matter. Can anybody think of an example of something that is not matter?
The empty space between the particles and atoms.
The empty space, yeah, because it's nothing, right?
Yeah. So
Anybody else?
Are mostly empty space.
What about love? Ideas? Emotions? Are they real?
Yeah.
Well, heck yeah, they're real. But they're not matter. They matter, but they aren't matter, right? What about energy?
Yes, that is.
Energy is not matter.
You can't photons.
But there's an interaction between energy and matter. And then when you get into the quantum stuff, you've got the electron behaving as a particle and as a wave, and that's where things kind of break down. But we're not going to go there yet. Okay? So matter occupies space, has mass. If we're talking about a particular kind or instance of matter, we call that a substance. So substance is the more general word. It could refer to an element, a molecule, atoms, a mixture, Diet Coke, donuts, a substance, right? Like substance abuse could be any of a number of substances that you're abusing, right? So we can classify matter in different ways. We can classify it by its physical state, its physical form, or by its composition, what kinds of things make it up, right? So classifying matter by its physical state, the three major physical states are solid, liquid, and gas. And so here we have examples of these three different states. The state of matter can change. A solid can change into a liquid can change into a gas. You can even have a solid changing directly into a gas. Any of these transitions are possible. Now this is, some weird green stuff, but the one substance that we are familiar with in all three states is water, right? We have different names for it. When water is a solid, we call it ice or snow, right? When water's a liquid, we call it water. And then when it's in the gas state, we often ignore it, but that is the moisture in the air, humidity, right? There are individual gas molecules, water molecules floating around in the air. And so that's in the gas state. When you have steam coming off of a pot of boiling water, that is water in the gas state. Actually, I'm just going to talk about these next few slides on this picture. So we can look at the particles in that matter and see how they relate to each other in the different states. So in a solid, the particles are packed very close together, and they're not moving relative to each other. And so we could also use students as an analogy for solid, liquid, and gas. So right now, this room is in the solid state. Students are in the solid state because you're sitting in chairs and you're not milling about, right? Now, are you perfectly still? I hope not. I hope everybody's breathing, right? Yeah, everybody's breathing. Some of you are fidgeting, wiggling. Understandable. I would too. It's kind of boring. But you're not moving relative to each other, and you're touchingly close. You could literally reach out and touch someone, right? So when a solid changes into a liquid, the particles are still touchingly close. What's different now is that they're able to slide and move relative to each other. So the liquid state of chemistry students happens during lab, where you get up and you go to the balance and you go over to the hood and people are milling about. We're still close together, we're in this same space, but we're moving relative to each other. In the gas state, the particles are completely separated from each other. They're far enough away they can't touch each other, they're not interacting with each other, and they're going to just spread out in space. And so for students, that would be like when class is over, and everybody goes out the door, you guys go off in all different directions, and most of you won't see anyone from the class until you come back to be solid students on Thursday, right? So solid matter packed closely together, atoms and molecules can vibrate, wiggle, but they don't move around. So a solid is going to have a fixed volume and a rigid shape, like ice cubes, right? You take an ice cube out of the tray and you put it on a plate, it's got the same shape, got the same volume. It's not going to change. And then, we could categorize or classify solids based on how the particles are arranged. So we can talk about crystalline solids. Those are solids that have a repeating pattern to the particles in them. And so right now, you guys are a crystalline solid student set, right? Because you're in rows of students in your chairs. Other solids are amorphous. And the prefix A means not or without, and morphous refers to shape. So amorphous, without shape. Examples of this would be things like glass and plastic. If we're talking about students, let's go a little younger and talk about kindergartners, and they're coming to sit around the teacher for story time. And they just plop down on the rug, and they don't sit in straight lines, right? They just plop down everywhere. So that would be amorphous. If we didn't have chairs and we were just going to all sit down on the floor, that would probably happen with us too. In the liquid, the molecules are still close together, but they're free to move. And so we see that liquids have fixed volumes, but not fixed shapes. So you take a cup of water and you pour it into a bowl. The shape of the water changes, right? But the volume of the water doesn't change. If you pour it back in, it's still that same volume, right? In the gas, there's lots of space between the particles. They're free to move. And because of this empty space, gases are compressible. So here we have two piston assemblies. Here, this one has a liquid in it. I'm sorry, a solid. It says solid right there. It says a solid in it. If you put pressure on this and try to compress it, you can't, because the particles are already as close together as they can get, right? But if you have a gas, there's lots of empty space. And if you press down on the piston, you can squeeze them closer together because there's empty space. Now, can anybody think of a solid that appears to be compressible?
Yes. Non-Newtonian liquids.
Non-Newtonian liquids.
So it's like the starch with water. It's like a slab.
But it's not a solid.
But it's also not a liquid.
Okay. But is it compressible?
Yes.
Let's think about an everyday thing.
Jello?
Jello?
Is that technically
Jello is technically a solid, right? But can you squeeze it and make it smaller? Yeah, you can squish it and it like kind of squirts out, right? What about something like a sponge?
Yeah, I was about to say a sponge.
So you have a sponge and you squish it and you can make it smaller. Well, is that violating this idea? No, because what's characteristic about a sponge? It has a whole bunch of holes in it, right? It's not, the entire sponge is not solid. It is composed of solid around spaces of a gas. And so when you compress a sponge, what you're doing is you're squeezing out all the gas that was interspersed with it. So solids are not compressible to any significant degree. Okay, so I'll just tell you there's some things I'm going to lie to you about. Because there's a lot of things that we can say, well, this is this way most of the time, right? There's exceptions, and a lot of those exceptions are not important in general chemistry, and so we ignore them, okay? But could you have a solid that's compressible? Well, you probably could. I can't think of one, but so most of the time. Okay, so that was according to physical state. We can also classify matter by the composition. What are the parts of it? So here we have matter, and we can ask ourselves, well, is the composition variable or is it always the same? Well, if the composition is always the same, then that's what we call a pure substance. Water is an example of a pure substance. Not tap water, but actually just water. It's always the same. So from a pure substance, then we can say, well, could we separate it into simpler substances? For something like water, the answer is yes, because there are hydrogen atoms and oxygen atoms, and those can be separated. You can do that as simply as just dropping a 9-volt battery into a glass of tap water. And you will see bubbles forming, and those are oxygen on one terminal and hydrogen on the other. And so you're breaking the water into hydrogen and oxygen, simpler materials. So that is a compound. If you can't break it into simpler substances, then it's an element. So an example here is helium, which is what they fill blimps and dirigibles with, or birthday balloons, right? Helium is composed of helium atoms, and you can't just break them down into smaller pieces. So these building blocks are just single building blocks, and they're all the same. Here, what we have in the compound is we have these little units that are composed of 2 or more of those building blocks. But each of these units, each of these particles or molecules is the same as the other ones. Well, what if the composition is variable? Then we have a mixture. So if we took hydrogen gas and oxygen gas and mixed them together, we could have a 50-50 mixture or a 20-80 mixture or an 80-20 mixture. You could get different amounts of hydrogen and oxygen. So that's a variable composition. Is the mixture uniform throughout? Is it the same on the top and the side and the middle and the bottom? Is it uniform? Then it's called homogeneous. The prefix homo meaning the same. So an example here is tea with sugar in it. You've got your tea and you dissolve the sugar in, you stir it up, and you could test that by tasting it. Taste the top, taste the bottom, taste the middle. It all tastes the same sweetness, right? A heterogeneous mixture is not uniform throughout. So an example of this is wet sand. So you have water, right, and sand. You can see there's a difference between them. One's a liquid and one's a solid, for goodness sake, right? And it's a variable composition. You could have a little bit of water in your sand or a whole lot of water in your sand. Variable composition, right? It's heterogeneous because there are two two or more obvious kinds of things. Okay? Any questions? So this is like details. So pure substance, only one component, composition is always the same. Mixture is two or more different components mixed together, right? And you can mix them in different ways. The pure substances we can break down into elements or compounds, depending on whether you can take that pure substance and separate it into simpler things. An element cannot be broken down into simpler substances. Those are the building blocks of matter. They're going to be atoms, like an iron atom or a helium atom. So the individual Lego bricks, when you take them all apart, those individual Lego bricks, with your bare hands, you cannot make them into simpler things. Now, could you take a hacksaw and cut the brick in half? Well, sure you could. But that's like nuclear chemistry, where you're taking the atom and you're smashing it, right? That's not normal stuff. So we're not talking about that here. But the atom is basically, without getting into nuclear chemistry, it's indestructible. You can't break it into smaller things. Whereas a compound is going to have two or more elements that are combined together. Mixtures can be heterogeneous or homogeneous, depending on how uniform they are. And this is another place where this is not a black and white thing, because it depends on how closely you're looking at the substance, right? So there's kind of a muddy area in the middle here. Heterogeneous, you've got composition that varies from one region of the substance to another, salt and sand, or maybe something like chicken noodle soup, right? There's noodles. You see, well, that's the noodle, and there's the chicken, little tiny piece of chicken. And there's the broth, right? And maybe they threw carrots in there to make it look pretty. You can see the different things. Versus a homogeneous soup might be something like cream of tomato soup, where it's all blended together, right? And you just see this, it looks uniform, right? It all looks the same. Okay, so that would be a homogeneous mixture. So when you make the soup, you could add more tomatoes or fewer tomatoes. The composition is not always going to be the same. Okay, so this is a question to help us know if we understand that. So in these images, a blue circle represents an atom of one kind of element. A red square is an atom of a different type of element. Which image is a pure substance? I've heard A, and I've heard none of them. So let's think about that. So in a pure substance, all the particles are the same. And it might not be clear. What they mean by this line here is that the blue circles and the red squares are joined together. So all of the individual pieces of this are a blue circle and a red square. Blue circle, red square. So all of the particles are the same. And so that would tell us that that is a pure substance. So A is a pure substance. So then what would we call B? If it's not a pure substance, it's a mixture, right? So the mixture, we have two different kinds of particles. So we've got the red squares and we've got the blue circles. This one is also a mixture. One of those is more homogeneous and one is more heterogeneous. Which is the more heterogeneous one, B or C? C is more heterogeneous because it's separated into sections, right? This top part is all blue circles. The bottom part is red squares. Here, this, you could say, looking at that, well, it's not completely homogeneous. Well, it's on the homogeneous end, right? So homo, the same, it looks the same all around. It looks like one thing. Hetero is different. You can identify different parts of that substance. Okay, so there will be a question on the test saying which of these is heterogeneous. So something about mixtures is that we can separate mixtures into their components because the different components are going to have different properties. They'll have different chemical properties, different physical properties. So here we're going to talk about separating mixtures based on differences in physical properties. So there's different techniques. One that we will be doing in lab several times is called decanting. So this is where you can separate a solid from a liquid. So think of a glass of sandy water, right? If you leave it alone, the sand will settle to the bottom and the water's on the top. Well, the water is a liquid, the sand is a solid. If you pour it carefully, the water will come out of the beaker and the sand won't. And so you can separate that mixture. Another way you can separate a mixture is through distillation. This is an old-fashioned distillation setup. This is what people who made moonshine during Prohibition were doing out in the woods. They would have a still, right? They were distilling the stuff they had fermented to get the alcohol out of it. So this is separating liquids based on how volatile they are or what their boiling point is. So if we had a mixture of ethanol and water in this flask and we heat it, the ethanol is going to vaporize, go into the gas state at a lower temperature than the water does. And so we're going to get ethanol vapor coming up in this tube. And we put a stopper here because we want to keep it, right? And this is the good stuff. And so then we're going to run it through this tube. This is called a condenser. And this area of the tube is double walled, so you can run cold water. The cold water is surrounding the tube and cooling it without actually getting in there. So as this ethanol in the gas state comes through here and cools down, it condenses back into a liquid, and it runs down in here, and you can capture it. Eventually, all of the ethanol would come out, and water would be left. Now that's where things get a little, if you're talking about real life, the very end separation is pretty tough. But that's the idea of distillation. Filtration. Anybody make coffee this morning? Making coffee, most methods, uses filtration. So here you're separating an insoluble solid, the coffee grounds, from the liquid, right, by filtering. You're passing this mixture of solid and liquid through a funnel, typically with filter paper. And we actually use coffee filters, right? The filter allows the water to go through because the molecules are small enough to go through the pores of the filter, but the coffee grounds stay behind. This is also what you're doing when you drain your spaghetti, right? You're filtering the spaghetti out of the water and separating them. Any questions?